Question 14. This states, write a vector equation and a scalar equation for a plane. So not a line, a plane. All right, so let's look at the solution. So the vector and scalar equations of a plane are shown. So a vector equation of a plane, so you can write it like this. The vector one is just going to be the this normal vector dot. Then you have this this vector on the plane r minus r naught with that position vector, and then the dot product of it is equal to 0. In other words, it's perpendicular to this point, to this vector connecting from this point to this point, and it's perpendicular, so hence the dot product is equal to 0. So then you could just write it like this. And you can also separate this up, so r you can also write this as r dot minus n vector times dot r naught, and then move this over to the other side. This is the negative. So you could also write it like this: n dot r equals to n dot r naught. So you can write it like that. Just epic stuff there. So dot product with this vector and this. And again, it stems from the dot product of this and this are perpendicular, and dot product is 0. In the scalar equations, the scalar equation is actually taking the dot product. So remember, this n is equal to abc. So then, so the dot product is going to be a times it by, the next one is going to be r minus r naught for the x component. It's going to be, that's just going to be x minus x naught. Then the dot product is, so a times x minus x naught. The next one is going to be b times it by the y components. Oops. Yeah, so the y components like that. So then b times y minus y naught. Last one is z over the c times it by z minus z naught. And they all equal to 0. Dot product is equal to 0. So yes, that's quite amazing stuff there.